Welcome, doctors. You dedicate your lives to understanding the intricate complexities of the human body, to diagnosing the unseen, and pushing the boundaries of medical science. Today, we're going to explore a different kind of complexity, the world of computing, and a revolutionary shift that's on the horizon: quantum computing. For decades, computers, including the powerful AI systems you might be encountering in medicine, have operated on a very basic principle: bits. Think of a bit like a simple light switch. It can be in one of two states, on or off. In the language of computers, we call these states 1 and 0. This is binary code, the fundamental language of all traditional computing. Now, these bits are often grouped together into sets of 8. We call a group of 8 bits a byte. Bytes are like letters in the alphabet of computer language. They represent numbers, text, instructions, everything a computer processes. Your patient records, medical images, AI diagnoses, at their core, they're all built from these bits and bytes. Current AI, even with its incredible abilities to analyze medical images, predict patient outcomes, or accelerate drug discovery, still relies on this binary system. It's incredibly powerful, but it has limitations. Think of it like trying to map the entire human genome using only black and white. You can get a lot of information, but you're missing a whole spectrum of possibilities. Enter the qubit. This is where things get truly fascinating, and where the rules of physics fundamentally change the game. A qubit, unlike a bit, isn't just limited to being a 0 or a 1. Thanks to the wonders of quantum mechanics, a qubit can be both 0 and 1 at the same time. Imagine a coin spinning in the air. It's not heads, and it's not tails. It's in a state of superposition, a combination of both possibilities simultaneously. A qubit is similar. It exists in a probabilistic state, a blend of 0 and 1 until we measure it. Now, this might sound abstract, even a little strange, but this ability to exist in multiple states at once is what gives qubits their incredible power. It's rooted in the bizarre but incredibly well-tested world of quantum physics, the science that governs the behavior of matter at the atomic and subatomic level. Quantum physics tells us that at the smallest scales, reality isn't as clear-cut as our everyday experience. Particles can be in multiple states at once, and they can be entangled, meaning their fates are linked, even across vast distances. Scientists harness these quantum phenomena to create the qubit. So, how do we actually build a qubit? Well, it's cutting-edge technology, and there are several approaches. One common method uses superconducting circuits. These are tiny electrical circuits cooled to incredibly low temperatures near absolute zero. At these temperatures, materials become superconducting, meaning electricity flows with virtually no resistance. These circuits can be engineered to exhibit quantum behavior and act as qubits. Another approach uses trapped ions. Here, individual atoms, ions, are trapped and controlled using electromagnetic fields. The quantum states of these ions, their energy levels, can be manipulated to represent qubits. Other materials and methods are also being explored, like using photons of light or even defects in diamonds. The key is to find systems that can reliably maintain these delicate quantum states. It's a bit like trying to isolate and control individual atoms, a truly remarkable feat of engineering. Now let's talk about why qubits are such a game changer for computing, and how they can exponentially improve performance. Remember bits? Each bit can be 0 or 1. 2 bits can represent 4 states: 0, 0, 0, 1, 1, 0, and 1, 1. 3 bits can represent 8 states, and so on. The number of states grows linearly, but with qubits, because of superposition, each qubit doubles the computational space. 1 qubit can be in 2 states simultaneously, 2 qubits can be in 4 states simultaneously, 0, 0, 0, 1, 1, 0, 1, 1 all at once. 3 qubits can be in 8 states at once, and so on. The number of states grows exponentially. This exponential scaling is the quantum advantage. For certain types of problems, especially those involving massive datasets and complex simulations, areas crucial to medical research and diagnosis, quantum computers have the potential to be vastly faster than even the most powerful classical computers. Think of drug discovery. Simulating how a drug molecule interacts with a protein in the body is incredibly computationally intensive for classical computers. Quantum computers could potentially perform these simulations with unprecedented speed and accuracy, dramatically accelerating the development of new therapies. Personalized medicine, analyzing vast genomic datasets to tailor treatments to individual patients, optimizing treatment plans. These are all areas where quantum computing could revolutionize healthcare. Quantum computing is still in its early stages. It's not going to replace your laptops or hospital servers anytime soon, but it represents a fundamental shift in how we compute. It's a move from the binary world of bits to the probabilistic, superposition-rich world of qubits, powered by the mind-bending laws of quantum mechanics. For doctors, understanding the potential of quantum computing is crucial. It's not just about faster computers. It's about unlocking new possibilities in diagnosis, treatment, and our fundamental understanding of life itself. The quantum revolution will significantly improve our existing capabilities in nanobioparticles, gene therapy, radiology, drug discovery, to name a few.